change from object A's frame of reference to object B's frame of reference. We're going to subtract B's velocity from each object in A's frame of reference. Huh? Alright, it's so much easier just to see it in action. So, bullet's velocity is 5 meters per second to the right in the Earth frame. The meter's velocity is 1 meter per second to the right in the Earth frame. To transform into the meter frame, we're going to subtract the meter in Earth speed from the bullet in Earth speed. So it appears to the meter to be 4 meters per second. The velocity of the bullet in the meter equals the velocity of the bullet in the Earth frame minus velocity of the meter in the Earth frame, giving us 4 meters per second. Excuse me. This is exactly how the meter sees the bullet moving. Velocity is 5 meters per second in the Earth frame. The meter's velocity is negative 1 meters per second in the Earth frame. Remember, subtract. To transform into the meter frame, we subtract the meter in Earth speed from the bullet in Earth speed. 5 minus negative 1 gives us 6 meters per second on the thing. In the Earth frame, the 4 cars shown above have the following velocities. Green car is positive 2 meters per second. It's moving that way. Blue car moving that way, 3 meters per second. Red car that way, 4 meters per second. And then yellow car opposite direction, 5 meters per second. To transform into the green car frame of reference, we're going to subtract the green car's velocity, 2 meters per second, from each car's velocity. So, to the green car, get ready. Hold on to your hats for this one. To the green car, you are not moving. But the blue car is moving 1 meter per second, the red car is moving 2 meters per second, and the yellow car is moving 7 meters per second in the opposite direction. So it appears to be faster. When you are in the car, it appears that nothing in the car is moving to you. You see the background moving, the trees going by, the lights, buildings, and all that stuff. So you know that you're moving. You kind of feel that you're moving. You feel the vibrations. But if you were to just ignore the vibrations and ignore the outside stuff, then it appears like you are not moving. Here we go. Going for a ride. Field trip time. Ready? Are we moving? In this frame of reference, we're not moving relative to each other. We see the background and stuff moving, so we know that we are moving, but if I can do this and allow the proper amount of light to come in, alright, there's my eyeball. Am I moving? Am I moving? There's no way of knowing because you're moving with me. But when I remove the hand, you get the background and you see that we are in fact moving. I've always been really fascinated with that. It's so cool. Things in your frame of reference are not. To go into the blue's car, we're going to subtract the blue car's velocity. So now the blue car, apparently to itself, is not moving. We're going to subtract 3 meters per second from each car's velocity. So here we go. Green car becomes negative 1 meters per second. That's why we're able to pass it. Even though in the original, we see the green car is just moving and the blue car is catching up to it, but the red car is catching up to it a lot quicker. Okay. So it's green car, blue car. There we go. Red car, 1 meter per second. Yellow car, negative 8. So that the faster we're going in this direction, the faster the oncoming traffic appears to us. We've seen it. When you're driving, you can't really tell how fast those cars are going. You can't tell if those cars that are moving past us in the opposite direction are speeding or not. It doesn't matter if they're speeding. Whatever they're doing is going to seem super fast to you. That's why head-on collisions are so dangerous, and we're going to look at that a little bit more with our note packet. For the red car is now not moving. Meanwhile, the blue and the green car are moving in the negative direction, and the yellow car is really flying by in the negative direction. But if we look at it from the yellow car's frame of reference, everybody else is going super fast, not us. Everybody else is going in the opposite direction of us. We're not moving. Everybody's going that way. Okay. So make sure you notice that each object stands still in its own frame of reference. The green car doesn't move in the green, the red car has zero velocity in the red car's frame. Two cars see each other going the same speeds in their own frame of reference. So just like I did with the camera, where I moved you with the same speed as me, we're in the same frame of reference at that point, so you can't tell if there's movement. Blue car sees the yellow car going 8 meters per second to the left, and the yellow car then sees the blue car going 8 meters per second to the right. So when I removed the hand, you could see that I was spinning around. Was I spinning around, or were you spinning around? Depends on who you ask. And then the green car sees the red car going to the right, and the red car sees the green car. Boost! Mario. Suppose that you can run at 5 meters per second. You're going to run to one end of a 400-meter conveyor belt, then back. This is a situation, if you've ever been to Universal Studios, then you've walked there from the parking garages, and when you're walking there, they have the moving sidewalks. This is the moving sidewalk effect. So hopefully you've played around with it and you've noticed it. When the belt is turned off, it doesn't move. When the belt is turned on, the surface moves at, let's say, 3 meters per second. So what does that look like? Belt off on the top, belt on the bottom. So the top animation, you're going 400 meters at 5 meters per second to the right. So it takes 80 seconds to the right. It then takes 80 seconds to go to the left. So it takes 160 seconds for the total trip. Your average speed is going to be 5 meters per second. This makes sense if you were running 5 meters per second for the whole time. So in the bottom animation, your 5 meters per second is added to the belt's 3 meters per second, so you go 8 meters per second when running to the right. So it's 50 seconds to the right. Then when you go to the left, you have to subtract that 3 meters per second from your 5, so now you're going 2 meters per second to the left. So it takes you 200 seconds to go to the left. Average speed of 3.2 meters per second. This is, your speed was 8 meters per second, then 2 meters per second. Shouldn't that average to 5 meters per second? Remember, it depends on how much time you spent moving in that. That was way back from 1.1 or 1.2 or something. Other examples of boost. So for this is how races are won. For swimming races, for example. It's not the person who's moving the fastest at any given point. It's the person who has the greater average speed. So if you are super fast off the blocks and you are slow to come back, then you're going to lose the race because you have to have the highest average speed.